All right, guys, we're starting a new chapter here, and chapter 7 really focuses on exponential growth and decay, which is something a little bit different for your mind to think about. We're going to do a little activity in class to try to teach you the difference between thinking linearly and thinking exponentially, okay? And that's just more useful when we are kind of talking about that, showing you visual examples in class. We're going to do that in class together, okay? But this is just the introduction to exploring different type of exponential models, okay? So what we're going to be dealing with are all the things that we're going to work with in this chapter are going to be in the form y equals a times b to the x, okay? Where a and b are numbers, and x is your variable. Okay? Now, when we're doing these, I don't have any door stops. Sorry about that. When we're doing these, okay, well, let's learn about what these three different letters here are called, okay? Whatever the exponent is attached to. So the x is obviously the exponent. Okay, whatever the exponent is attached to, that's what's called the base. Okay, so whatever the exponent is attached to is called the base. The letter out in front, this is a word you already know, this is the coefficient. Okay, all right, so examples of something like this could be 2 times 3 to the x. Okay, could be, let's see, 6 times 1/2 to the x. Okay. Now, I want to talk a little bit about what happens to a simple graph. Let's just talk about the equation y equals 2 to the x. Okay. Let's first think about what values could come up in this. We want to talk about domain and range. Okay. Let's first talk about the domain. The domain is what values can be plugged in for x. The domain for these is always going to be all real numbers, okay? And that's because there is no rule in math that says that a certain type of number cannot be an exponent. 0 can be an exponent, negatives can be exponents, positives can be exponents, decimals can be exponents. So I can plug any number I want here in for x, okay? My range is where we are going to maybe get a little bit more tricky, okay? And we can use our calculator to look at the range here. First, let's think about this. Let's look at the graph, I guess, first. 2 to the x. Now, notice just by looking at this that this graph never gets negative. Okay, why does it never get negative? What's happening here? Well, let's look at our table of values so that we can kind of understand that. Okay. First of all, notice that as our x gets bigger, again, we're focusing on y equals 2 to the x right here. As our exponent gets bigger, as our x gets bigger, our y is getting much larger. 2 to the 10th, as you're looking right here, 2 to the 10th is 1,024. And as I get higher, look at that, 2 to the 17th is 131,072. Okay? Well, now the question is, what happens as I get lower? Look, now I'm getting into these negatives, and look, excuse me, look how the number is getting smaller and smaller and smaller. Now, this e to the -4th, that means it's scientific notation. That means that it's a very small number. Okay, why is that the case? Why is, let's use this. Why is 2 to the -4 power? Why is that a super small number? Well, let's remember about our negative exponent rule. Negative exponent says that first of all, remember that thing's on the top of a fraction. It's in the numerator right now. If something has a negative exponent, you can move that something to the bottom of the exponent or the fraction and make the exponent positive. So this is really 1 over 2 to the 4th, 2, 4, 8, 16, which is really 1 over 16, a very small number, right? As my negative numbers get larger, the answer gets infinitely smaller, but it will never reach 0, right? Because 2 to the negative, let's say 999, okay, is still why it's still 1 over 2 to the 999. It's still 1 over a very large number, which is still something that's very, very small, but it's not zero. It is something, okay? So my range here, my y's, again, looking at the graph here, my y's are always going to be, not always, but in this case, going to be greater than zero. It will never actually touch zero because I'll always have a little bit of a number here and they'll always go up. Now, we can talk about how are you going to find this part of the graph here where this graph is flattening out. It's getting as close as possible to zero without actually touching zero. That is what's called an asymptote. Okay, an asymptote is a line that a graph approaches but never touches, because it can't actually ever get to that number. Just like in this example, we're never actually being able to get to zero. We can get to be the smallest number of all time, but we can't get to zero, okay? Good, hold on, I'm just making sure that I hit everything here, okay? Now let's talk about how to identify the difference between a growth and a decay. Look how this value, as my x's are getting bigger, my y's are getting bigger. That's a growth. If my x's get bigger and my y's get bigger at the same time, that's a growth, okay? Let's see what the graph of something like maybe 2 times 0.5 to the x. Let's see what that looks like. Now notice, as my x's are getting bigger this time, my y's are getting smaller. As the graph is going to the right, the graph is getting smaller. As my x's are getting bigger, my y's are getting smaller. That's a decay. A decay means that as my x's are getting bigger, my y's are getting smaller. Well, how can you tell the difference between a growth and a decay? By just looking at the equation. It's all about the base, okay? If the base is greater than 1, then it's a growth. If the base is between 0 and 1, oh, I don't want or equal to there, sorry, then it's a decay. All right, so I guess let's go through a couple. 2 times 3 to the x, that's a growth because the base is greater than 1. 5 times 3/4 to the x, that's a decay because the base is between 0 and 1. 1/2 times 6 to the x, that's a growth because the base, it doesn't matter about the coefficient, that's a growth because the base is greater than 1. How about 5 times 0.8 to the x? That's a decay because the base is between 0 and 1. Okay? Let's see. Just checking to make sure I'm not leaving anything out here for you guys, okay? Okay, the only other thing that they're going to have you do here in these, other than finding the domain and range, okay, is they're also going to have you find the y-intercept, which is always an important aspect of a graph, okay? To find the y-intercept, or really to find any intercept in math, you plug 0 in for the other letter. So in this case, to find the y-intercept, I'm going to plug 0 in for x. Okay, I could do that in any of these examples. So if I wanted to find the y-intercept of this problem here, okay, I would just plug 0 in for x. 2 times 3 to the 0. Well, anything to the 0 is 1, so this is just 2 times 1, which is 2. The y-intercept here is at 0, 2. Okay. Here, again, if I want to find the y-intercept, I plug 0 in for x. It'd be 5 times 3/4 to the 0. Well, anything to the 0 power is 1. So that's 5 times 1, which is 5. The y-intercept would be at 0, 5. I think you're seeing the pattern. The y-intercept is usually, it is the coefficient that's in front, okay? But that's not always true if you have plus and minuses. So like for instance, if you had something like 2 times 4 to the x minus 6. Now this is going to throw off that the coefficient is the y-intercept. So here I have 2 times 4 to the 0 minus 6. 4 to the 0, of course, is 1. So I have 2 times 1 minus 6, which is negative 4. So my y-intercept is at 0, comma, negative 4. Okay? Other than that, all it's going to have you do for these types of problems is graph them. We can do one of those very quickly. Let's say it wants you to graph 2 times 3 to the x. Okay, what you'll need to do is just make a t-table of values and use your calculator to help here. All right, so you have 2 times 3 to the x power. I'll graph to take a look at it. I'll go to the table to get down some values with some numbers that I can really fit in, okay? So I've got negative 2 and 0.2. I'm picking out some numbers here. 0, 2, 1, 6. Those are what fits on the graph. So I have negative 2 and 0.2, 0, 2, 1, 6. Okay, I have those 3 accurate dots. Once I have those, you need at least 3 accurate points. Once you have those 3 accurate points, you can draw the general shape of the graph going through those points. Now notice how my graph on my calculator got close to this asymptote, but never crossed. Okay, and so does this. If you draw this graph crossing the x-axis, then your graph, of course, is wrong. Okay. All right, that's all I got for you today. We will move on as quickly as we can here through chapter 7. All right.